Hello, in this video I'd like to talk about axiomatizing the weak second-order theory of one successor. Remember that we're interested in studying the non-standard models of weak S1S, and so in order to do that, it's going to be really convenient to have an axiomatization of weak S1S. Technically, you can do this sort of stuff without having an axiomatization, but it makes things really convenient for proving that various structures are non-standard models. When I'm talking about an axiomatization, I'm talking about a complete axiomatization. I'm talking about a set of formulas from which all true facts about the standard model in this particular logic follow. And so any other structure that also satisfies these axioms must also satisfy all of these other true things about the standard model. All of the true things about the standard model. So that's the trick. Even though it's a bit of work to show that a particular set of formulas is an axiomatization, this saves us the trouble of having to prove that all formulas are true of our proposed non-standard models. Now we only have to prove that our axioms are true of our proposed non-standard models. So it saves us work in the long run. Now, I'm not the first person to axiomatize the weak second-order theory of one successor. This was done in the 70s by Seifkes, but his axiomatization was based on induction. This has some advantages and some disadvantages. One of the big advantages of an induction-based axiom system is that you can have a very small axiomatization alongside induction. Right, your axiomatization can look like maybe 2 or 3 axioms to kind of set things up, and then your induction schema axiom. Of course, your induction schema axiom is actually secretly one axiom for every possible formula in your language, so it's technically an infinite, a countably infinite axiomatization. But we'll see that that's actually unavoidable in the case of weak S1S. So we don't need to worry about that. When I say that induction-based axiom system is small, I mean that it's very easy to present to people, right? Again, it's like 2 or 3 axioms, and then your induction axiom schema, which again, it gives you an instance of an axiom for every possible formula phi, but super easy to write down. It's also very easy to prove stuff from this axiomatization. Induction is a very assertive axiom. It's asserting that induction works for every possible formula. So it's saying a lot of things. And a lot of the basic facts about weak S1S can be proved just using induction. You just have to figure out what the right variable to induct over. And then very often the inductive step and the base step are super easy, super straightforward facts to prove. On the other hand, induction-based axiom schema conceal their exact power. Here we have an axiomatization of piano arithmetic, which is a subset of all true facts about the natural numbers with addition and multiplication. You can't actually, there's no nice axiomatization of that structure as a whole in terms of its first-order logical properties. But piano arithmetic is very robust, and it allows us to prove a lot of facts about the natural numbers with addition and multiplication. And it has an axiom schema of induction that gives us an axiom for every formula that you can write down in the first-order logic of the natural numbers with addition and multiplication. As we've seen in that particular logic, we can talk about the operation of Turing machines. And so this is actually a very assertive axiom schema. And piano arithmetic has tons of facts in it. It's very difficult to reason about, to determine whether a fact is true or false, because again, all of that boils down to sometimes having to figure out if a particular Turing machine halts or not. And of course, piano arithmetic is subject to Gödel's incompleteness theorem. On the other hand, here we have an axiomatization of Pressburger arithmetic involving induction. And it looks very similar. The key difference in these axiom systems is that in Pressburger arithmetic, the types of formulas that this induction is an axiom schema over are just formulas involving addition of natural numbers. And that's the key difference. Even though these axiom systems look really similar to each other, the fact that in Pressburger arithmetic we have an induction axiom for a smaller and less expressive set of formulas means that Pressburger arithmetic is much less robust, and thus much nicer to study. In an earlier video, we were able to fully categorize the collections of tuples that we were able to describe in Pressburger arithmetic. And we also had a decision procedure for determining if a formula of Pressburger arithmetic was true or false. So it's a much less expressive but easier to study structure. And their axiomatizations look almost identical to each other. Weak S1S is somewhere in between these two systems, but that's really not something you can tell just by looking at an axiomatization that involves induction. As such, one of the things that I set out to do in axiomatizing weak S1S was to really get at the heart of what weak S1S is about, to construct a bunch of axioms based around finite state automata. The other difficulty of having an induction schema in our axiomatization is that it's hard to prove two. It's hard to prove that particular structures satisfy induction for all formulas within this collection of formulas. At least as far as I know. There might be an easy way to do it, but I'm not aware of one. And so when I set out to create the axiomatization that I'm going to present in this video, I had in the back of my mind that I wanted it to be really easy to prove that my proposed non-standard models actually were non-standard models, to make it very easy to prove that those structures in particular satisfied all of the axioms. So for instance, all of my proposed non-standard models have a first-order part that's a woozle. And so all I have to do is look up an axiomatization of the non-standard models of omega as a linear ordering and translate all of that into weak S1S, and I can toss all of those axioms into my axiom system, and even though it's going to be a lot of axioms, I can just check off all of them at once when asking, do my non-standard models satisfy this? Because we've constructed our non-standard models in order that their first-order parts be woozles. Remember that we have a notion of ordering in this structure where we say that x is less than or equal to y if every downwards closed set containing y also necessarily contains x. So I'm just going to use less than or equal to, but when I write that, remember that it's shorthand for this formula here. Let's actually write out these axioms, starting with the axioms of what it means to be a linear ordering. We have reflexivity, that any element is less than or equal to itself. This is a tautology. When we unpack this definition using this, it's provably true just using logical properties, not actually referring to any of the facts about this structure. So we don't have to include this among our axioms. Antisymmetry actually says something non-trivial. If every downwards closed set containing y also contains x, and every downwards closed set containing x also contains y, well, on the surface, it's not clear if x and y are the same. It might just be that the downwards closed sets aren't able to separate the two. That is, every downwards closed set either contains x and y, or doesn't contain x and y. They go together within the downwards closed sets. But the antisymmetry axiom says that can't actually be the case. If we have that situation, then x is actually equal to y. They're actually the same thing. And so in some sense, antisymmetry is saying that we can separate any two elements using a downwards closed set. We can find a downwards closed set containing one, but not containing the other. And of course, which way that goes depends on the ordering of the elements. Next, we have the axiom of transitivity. If every downwards closed set containing y also contains x, and every downwards closed set containing z also contains y, then every downwards closed set containing z also contains x. Again, this is a tautology. It follows from the transitivity of implication within this definition here. So again, we don't have to bother including this in our actual axiomatization. Totality, on the other hand, is non-trivial. It says that every downwards closed set containing y also contains x, or every downwards closed set containing x also contains y. Essentially, this prevents the kind of situation where we have x and y being on kind of separate tracks that eventually merge together, where we have a bunch of downwards closed sets up here and a bunch of downwards closed sets down here, and maybe eventually they join, but a downwards closed set containing y doesn't necessarily contain x, and a downwards closed set containing x doesn't necessarily contain y. This axiom prohibits this sort of situation. So that's our linear ordering axioms, and then we also want our woozle axioms. An important property of the woozles is that every element has an immediate successor, an element such that there's no elements between the two of them. And it's actually going to be important to kind of link that with our pre-existing notion of successor on the structure. Actually, one of the most important consequences of this axiom is one of the simplest, which is that x is not equal to the successor of x. Another important consequence of this is because x is not greater than or equal to s of x, that means that there's a downwards closed set containing x and not containing s of x. We like to call this set the downwards closure of x. Another important property of this structure is that it has no largest element, but that follows from the fact that we're closed under taking successor. For every x that's not equal to 0, we have that x is the successor of something. This is fairly trivial. Once we know that the set just containing the number 0 exists, this is a downwards closed set containing 0 and not containing anything else. And so if x is unequal to 0, then it's not the case that 0 is greater than or equal to x by the definition. So again, it's a ton of axioms here, many of which we don't actually need, but it's perfectly okay to just toss these in, and I'm going to toss them in as a single axiom here, which is just kind of the and together of all of these sub-axioms. And I can check off immediately that my proposed non-standard models satisfy all of these axioms because they were constructed in order that their first-order parts be woozles. The only thing we really have to check is that this notion of less than or equal to agrees with the notion of less than or equal to that is in the woozle. Next, I'm going to want a few set properties. The first set axiom that we're going to need is extensionality, that if we have two second-order objects, they're considered to be equal if and only if they contain the same elements. So we can't have two second-order objects that contain the same elements but are mysteriously different in some other way. Of course, if two elements are equal, then they do have to contain the same things. That's just kind of one of the logical properties of equality, is that if two things are equal, they should be logically interchangeable within any formula. And again, it's going to be really easy to check off this axiom when we construct a proposed non-standard model, because the second-order types in my proposed non-standard models are actually collections of elements of the first type. They're actually sets. But one can construct really weird structures that don't satisfy the reverse. One can have two second-order objects that contain the same first-order objects and not be equal to each other. The next axiom we need is a singleton axiom that says that for any first-order object, there's a second-order object that just contains that first-order object and nothing else. Again, this will be fairly trivial to check of our proposed non-standard models. Next, we have closure under union and set subtraction. From this, we get closure under intersection because we can write the intersection in terms of set subtraction. And in fact, together, this gives us closure under any Boolean operation that preserves boundedness. Because the second-order objects in our structure are supposed to be finite sets, they're not closed under complementation, so there's actually a bunch of Boolean operations that second-order elements in the structure are not closed under, but anything that you could expect it to be closed under It's closed under, and that actually just follows from closure under these two things. That's fairly similar to the proof that every Boolean operation can be written in terms of union and complement, for instance. This axiom here also gives us the empty set. We just take a singleton. Well, we have to know that there actually exists a first order element, but we know that because 0 exists. But once we know that there exists a first order element and there's a singleton of that first order element, so there exists a second order element, we can subtract that second order element from itself to get the empty set. Finally, I assert that every non-empty set has a maximum element to it. It's worth noting that there's a little bit of induction in this axiom here. One of the ways of thinking about induction is if there is a counterexample to a particular property phi, then there's a smallest counterexample to phi. This is, if you take induction and take its contrapositive, it says that if there is an x that doesn't satisfy phi, then either 0 doesn't satisfy phi, or there's some x where x doesn't satisfy phi and x minus 1 does satisfy phi. The negation of the base case and the inductive step, respectively. Of course, this axiom here isn't quite if there is a property phi and an element x satisfying phi, then there's a smallest element x satisfying phi. First of all, this is talking about maxima and not minima, so we're kind of like inducting backwards. The property that we're talking about here is membership in a set. So only properties that can be talked about in terms of membership of a set are actually like inductible using this axiom here. So it's certainly not as robust as a typical induction axiom, but we can do some induction-like tricks using this particular axiom here, and particularly when we flip it around and prove that every non-empty set has a minimum, this will give us kind of a sort of induction principle that we can use to prove all sorts of things. Our third axiom is going to be something that we've talked about a lot, which is closure under run maps. And this is actually going to be an axiom schema, an infinite collection of first-order logical sentences in our language, one for each automaton. And each one of them is going to assert that we're closed under the run maps for that particular automaton. Of course, it's important to remember what I mean by automata within weak S1S. Remember that we had a way of translating back and forth between automata and formulas within weak S1S. And so the result of translating an automaton into a formula is what I'm talking about when I'm talking about these automata here. Those formulas look something like this. So given particular second order elements, x0 through xn minus 1, we can talk about there existing an L that's going to be the length of the run, and yq0 through yqm minus 1. These are going to be sets that represent times where the automaton is in state q0 through qm minus 1. We're going to want L to be the least strict upper bound of x0 through xn, so we're going to take the union of these x0 through xn minus 1, take the maximum of that union, and then take the successor of that, and that's going to be L. So here I'm talking about full runs, starting at the start state and ending at the final state, and the runs are going to be of length 1 longer than the input is. The yq are going to partition 0 through L, that is for any x between 0 and L, it's in exactly 1 of the yq. 0 is going to be in the start state, and of course if we have multiple start states we can make sense of that, although for now let's assume we're working with a deterministic automaton. We're going to have a transition constraint. If at time x we're in state q, and the input is going to be which of these sets contain x and which of these sets don't contain x. That we can think of that as kind of like a binary sequence, And that's what's getting input into the automaton at time x. So given a particular state and a particular input, the state that we're at the next moment in time, successor x moment in time, is going to have to be given by the transition function for the automaton. And then finally, we're going to want to say that L is in some final state, right? At the end of the run, we're in a final or accept state. Although for most of this reasoning, we're actually going to drop this constraint because I'm only interested in talking about closure under run maps. I don't say that we have accepting run maps for every automaton. That isn't true. But every deterministic automaton does have a run given any particular input. That is true. And using this sort of language, we can express that, although really we can only express that. We can come up with a singular formula that captures all of this in first-order logic, but just for a single automaton. And so if we want to express that we're closed under run maps for all automata, we're going to need a separate axiom for each automaton. And that's what we have here. We have one axiom for each automaton. So this is countably many axioms here. And just like before, there's a little bit of induction hidden in here. We know that there's a partial run of length 1 that just manages what state 0 is in, what state we're starting out in. And then given a partial run up to x, we can augment it according to the transition function here to be a partial run up to x plus 1. Just by adding in successor of x into the appropriate state set. And what this is saying is that we can do this very specific type of induction up to L. We can find a run up of length whatever we need it to be. So again, our closure under run maps axiom is going to look something like this. I need to get rid of this constraint. I'm not going to assert that all automata accept all inputs, and I'm going to say that this is true for any x1 through xn minus 1. Now, our reasoning about decomposing run maps, we sort of get for free. And so we could have this axiom actually just be that the permutation automata and the 1-bit memory automata have run maps. For some reason, in my PhD thesis, I assert that we're closed under run maps for what are called runnable automata. These are automata that are at least deterministic. They have at least one start state, and given a particular state and a particular input, there's at least one state that they can transition to. For some reason, I assert that for all of these automata, we're closed under their run maps, and we don't really need that. We can always take one of these runnable automata, pare it down to a deterministic automaton, find a run of that, and that's going to be a run of the original automaton. So I don't know why I did that. Combining this axiom here with the axiom that every set has a maximal element, we can prove that every set has a minimal element. Let's consider for a moment a specific 1-bit memory automaton. So what we're going to do is we're going to read in the set X, and the way that I like to do this is I like to read it in as a sequence of zeros and ones. We'll put zeros in places where that element isn't in X, and we'll put 1 in places where that element is in X. And so if we read a 0, that is, we're in a position X where X is not in our set X, then the state doesn't change. And if we read a 1, that is, we're in a position X where that X is in our big X, then we change into state 1. The start state will be, of course, Q0, and we don't care about the final state because we're just going to use the fact that this automaton has a run on this particular input. When we do this run, we get a YQ0 and a YQ1 that look like the following. They're first of all going to partition the set from 0 to L, where L is 1 plus the maximum of X. Remember that X is non-empty, so it actually has a maximum, so we can just add 1 to that. The automaton is going to start in the start state, Q0, and then at every position, if W is in X, then the successor of W, we definitely have to be in state Q1. And if W is not in X, then we don't change which state set we're in. The way this automaton works is it's going to be in state Q0 until it encounters an element of X, and then it's going to switch into state Q1 and stay there. Of course, we have to prove from our axioms that it actually behaves this way. And I'm going to start by saying if we're in state Q0 at time z, and we have a time before that, then we're also in state Q0 before that. Well, suppose not. Then we can construct this concrete set, yq1 intersected with the downwards closure of z, and we know that that set is non-empty. Being able to do this construction here is important. We can only make use of our axiom that every non-empty set has a largest element if we actually know that that thing is a set within our model. And this shows some of the ways that we can assert that a set is a set in our model. It can either be one of our hypotheses that this is a set in our model, or this can be one of the basic sets that we know how to construct, or we can combine sets that we know are in our model using Boolean operations to get a new set that we know must be in our model. So this set must be in our model, and it has to be non-empty, and so it has a largest element. Let's call that largest element V. V can't be Z because we know that Z is in yq0, not yq1, and they're disjoint. So that means that successor of V is in the interval from 0 to Z. But because V is the largest element of this collection, we know that the successor of V isn't in this collection. And the only way that can happen is if the successor of V isn't in yq1, and so the successor of V has to be in yq0. And so we have a V that's in yq1, and successor of V is in yq0. If we look back at our transition diagram, that can't happen. So we have a contradiction. Once we have this fact here, we can show that the maximum element of yq0 has to be the minimal element of X. This here exemplifies the sorts of proofs that we can do within this axiom system. Essentially, we're trying to say that something weird doesn't happen, and so we have to be able to describe, using the operations that we're closed under, the positions where that something weird happens, and show that that set is empty because it can't have a largest element, or eventually a smallest element. When we have this, we can make use of it. So very much an inductive feeling sort of proof, and it's a little bit tricky because, this is obviously true. Like, obviously, an automaton should behave the way that we think it does. But that's only true in our standard model. The thing that we're trying to prove is that our notions of automata still work in our non-standard models. In our non-standard models, finite state automata still behave very nicely. They can't go from being in one state to another without transitioning from that one state to another. But it's a little bit harder to reason about these things because we have these infinite gaps where conceivably we could go from being in one state before the gap to being in another state after the gap without transitioning from the one state to the other at any one particular time. It's just that this sort of behavior is forbidden. Now that we have the fact that every non-empty set X has a minimal element, we can use this sort of as an induction axiom. We just have to show that the set of counterexamples to a certain assertion that we're trying to make, it forms a set within the model. This fact will tell us that there's a minimal counterexample. That minimal counterexample has to either be 0 or the successor of something, and we can rule out those two options using our base case and our inductive step. So for instance, one of the important facts about automata here is that deterministic automata have unique runs. That is, for any one specific input, x0 through xn minus 1, there's going to be a unique yq0 through yqm that satisfy the start state and transition relation of the automaton. Suppose not. Suppose instead we have a different run, zq0 through zqm-1, that also has a correct start state and also has correct transitions. Well, we can take the union of the symmetric differences of these two sets to construct a set which just has positions where the y runs and the z runs disagree with each other. By our assertion that z is a different run from y, at least one of these symmetric differences has an element in it. And so, because we know that these and their union are an element in our model, we know that they have a minimal element. That minimal element can't be 0 because 0 is in yq0 and 0 is in zq0. It's in the start state. Both of these runs start in the start state q0. So that minimal element has a predecessor where everything's going fine. These two runs agree. So at some position w, these two runs agree, and at position successor of w, they disagree. That doesn't seem to satisfy the transition function that we were talking about, right? This is a deterministic automaton. So that gives us a contradiction. We can't have two separate runs given a particular input. Again, this proof here exemplifies the sort of reasoning that we can do in this system. If we want to prove that a particular automaton behaves nicely, all we have to do is somehow describe, using sets that we already know exist and set operations that we know that we're closed under, the set of positions where it behaves not nicely. And then that set has a minimal element by this fact here. And we say, oh, well, actually, no, that can't be the case. The automaton was behaving correctly at the start, and if it's behaving correctly at a particular w, it's behaving correctly at the successor of w, and so that rules out the possibility of this set of positions where things are going wrong having a minimal element. One of the facts that we're going to want to prove from our axioms is that automata behave the way that we think they should. There are specific automata and automata constructions that should have very precise behavior. There's an automaton that can tell us if two sets are equal to each other. There's an automaton that can tell us if one input is the successor of another input. There's automata that we can construct to do complementation, intersection, union, and projection of the languages accepted by various other automata. And all our axioms really do is claim that these automata have runs, at least if we're talking about the deterministic version of these automata. It's up to us to prove that they actually behave the way that we think they should. Let's start with a really simple example, and this will allow me to also talk about what happens if we want to feed in a first-order element into an automaton. I claim that this automaton here, when fed in singletons corresponding to the singleton of x0 and the singleton of x1, tells us whether or not x1 is equal to the successor of x0. So this is how we can feed in first-order elements into any automaton, right? We just take their singletons, which we know exist by the singleton axiom, and feed those in to the automaton. Let's take a look at this automaton on a particular input. So here I'm going to feed in x0 is equal to 2 and x1 is equal to 3. Remember, we're representing those as sets, the singletons of those things, and then we're representing those sets as sequences of zeros and ones where there's a 1 in positions where we actually have an element in that set. And of course, all of these things, because they're finite sets, are all going to end with just a bunch of zeros. So the way this automaton works is it starts off in state q0, so 0 is in yq0, which we denote by putting a 1 here, and 0's everywhere else. Remember that the yq's partition the interval from 0 to L. I guess we should work out what L is. L is going to be 4. That's one more than the largest element of the union of the inputs. And so we're going to want these sets here to partition the interval from 0 to 4. Our transition function says that if we're in state q0 and we read a 0, 0, we stay in state q0. We do that again when we read this 0, 0. When we read a 1, 0, that's going to take us from state q0 to state q1. And then when we're in state q1 and we read a 0, 1, that's going to take us into state q2. That's going to be the end of our run because we've partitioned the set from 0 to 4. And L4 is in yq for some q which is an accept state. And so this automaton is going to accept. It's going to say, yes, indeed, 3 is the successor of 2. So this yq0 is the set 0, 1, 2. yq1 is the singleton 3, and yq2 is the singleton 4. This is our accepting run for this particular input. So how can we prove this? How can we prove that this automaton behaves correctly even given potentially non-standard inputs? Well, the proof is a little bit tedious, but here's how it can go. We use the linear ordering properties of the first order part to divide up into a bunch of different cases given particular inputs. Is x0 1 less than x1? Is it a bunch less than x1? Is it equal to x1? Is it more than x1? We divide up into a bunch of different cases. And in each of those cases, we construct the run of the automaton using the various operations that we know that our sets are closed under. These sets we know exist because of the singleton property, and if we have long runs like this on a long interval, we know that those exist because of the downwards closure property. And if we have an interval from one point to another point, then those exist because of Boolean combinations of downwards closed sets. So in each of the possibilities, we explicitly construct the run of that automaton, and as we proved before, the runs are unique. And so whether or not this automaton accepts this particular input depends exclusively on the final state of our automaton. Right? We don't have to worry about the run we construct not being an accepting run, but there being some other accepting run somewhere out there, because this is a deterministic automaton, so it only has a unique run. And so we simply show that this thing ends up in an accept state if and only if this relation holds for the inputs. We have one additional axiom schema that you might anticipate, which is that we're closed under reverse run maps. That is, if we have a reverse deterministic automaton, a non-deterministic automaton that has a unique final state, and given the next state and the current input, the current state is determined, then there is a reverse run of this automaton that may or may not have the correct start state, but at the very least you can start at the end and work your way towards the beginning in a deterministic fashion, and if you wind up in a start state, then there is an accepting run, and if you don't wind up in a start state, then there isn't an accepting run. Just like in the case of the forward deterministic automata, these automata have unique runs, and you can prove that again using the fact that, I guess in this case it would be using the fact that every non-empty set has a largest element. And this is it. I claim that this is a complete axiomatization of weak S1S. That is to say that any logical properties of weak S1S can be proved directly from the combination of our axioms. So how can we show that this is an axiomatization? First of all, it's important to check to make sure all of these things are actually true of the standard model, but that's fine. They're all true of the standard model. Our next step is going to be to define a canonical form for formulas in weak S1S, with the idea that every formula is equivalent to an equivalent formula in canonical form. And the way that we're going to do this is to take our formula, translate it into an automaton, and then translate it back into a WS1S formula. The corresponding formula will look like the sort of thing that we get when we turn an automaton into a WS1S formula, and it's going to be equivalent to the original formula. And better than that, we actually have a step-by-step procedure for turning a formula into its canonical form. Right? If we look back at our procedure for turning arbitrary WS1S formulas into corresponding automata, we wound up working through the formula from the inside out, translating inside bits into automata, and working our way out. So we started by first turning the atomic formulas into automata, and then we showed that, for instance, if we had the conjunction of two formulas, we could turn the individual formulas in the conjunction into automata, and then use our automaton conjunction operation to calculate the automaton for the conjunction of those two formulas. And we had a procedure for doing this for every way of building up a formula recursively. Now, it's worth noting that we're not actually interested in formulas. We're interested in sentences. Formulas with no free variables. Formulas can be true or false depending on the values of the free variables that you plug into them. But sentences are either always true or always false, and that's really what we are trying to capture with our axiomatizations. We want it to be the case that all true sentences are consequences of our axiomatization. Now, something interesting happens in the case of sentences when we translate them into canonical form, into automaton form, because the corresponding formulas are automata that don't take in any inputs. And so the definition kind of collapses. Here we have a formula that takes in no inputs. We'll still have our L and our YQ naught through YQ minus 1. L is again going to be the least strict upper bound of all of the inputs. What's the least strict upper bound of the empty set? Well, that's 0. And these state sets are going to wind up partitioning the interval from 0 to 0. A single element set. So the idea here is that one of these sets contains 0 and the rest of them are empty. And in particular, we already know which set has to contain 0. It has to be the set corresponding to the start state. And the question that our automaton is asking is L in an accept state? Well, L is 0. So the question is 0 in the set corresponding to some accept state? And the answer is, well, is the start state an accept state or not? If it is, then yes, and if not, then no. What we're going to want is we're going to want the behavior of this automaton to be a consequence of our axioms. And this actually uses very few axioms. It pretty much just uses the existence of singletons in the empty set. So we have that our axioms imply our formula when it's translated into canonical form. So if we have a true sentence and translate it into canonical form, we get a new sentence that's true, and its truth is a consequence of our axioms. Now, we're almost there. Our goal is to show that if we start off with a true sentence, that sentence is a consequence of our axioms. And so all we need to do is work our way up this sequence of reductions to get to our original sentence. We need to show that each reduction step, each thing that we could do to a sentence as we reduce it down into canonical form, each of those reduction steps takes a formula and turns it into an equivalent formula. and that this equivalence is a consequence of our axioms. That will tell us that our axioms imply that these two are equivalent, and these two are equivalent, and these two are equivalent, all the way up until we prove that our sentence is equivalent to our canonical form was provable from our axioms, and so our sentence is provable from the axioms. And actually, technically speaking, we don't need an if and only if, we just need the reverse implications. So that's it. That's our process for proving that our axiomatization is complete. So what do each of the steps of this proof wind up looking like? What we need to do in order to complete this proof is to show that our axiomatization implies that atomic formulas are equivalent to the automata that we expect them to be equivalent to. I've already done part of the work for this in this video, showing that the automata that we expect to correspond to atomic formulas with one successor in them wind up working the way that we expect them to, as a consequence of our axioms. Of course, if we're dealing with atomic formulas that have more than one successor in them, we should relationalize in order to break them apart into a bunch of separate atomic formulas, and then do the argument. As I mentioned before, we need to show that our axiomatization implies that our way of conjoining automata is valid. That is, if we have a formula in canonical form, in automaton form, and we conjoin that formula with another formula in canonical form, in automaton form, that's going to be equivalent to the formula for the automaton that we expect this to be equivalent to. Again, just using the basic construction that we did so many videos ago. Just like then, there's actually a really tricky situation in this step of the proof, which is if this formula and this formula have different sets of free variables. And the way to get around that is by reasoning about unbounded automata. Automata that are allowed to run beyond the end of the original input. We also need to show that our axiomatization implies that our procedure for translating formulas of the form there exists an X that makes a particular automaton accept is equivalent to the corresponding automaton accepting the rest of the input variables. When we did this construction, we found it most helpful to translate our automaton into an unbounded, non-deterministic automaton, at which point this was trivial. And then finally, we need to show that our axiomatization implies that the negation of an automaton, the automaton that we expect to calculate the complement of the other automaton's regular language, that this is an equivalence. We're assuming that the canonical form is bounded deterministic automata, so they're deterministic and they end at the end of the initial input. These automata are really easy to complement. You just take the complement of their accepting sets, and there you go. You have the automaton that we expect to be equivalent to the negation of the formula for the original automaton. As you might expect, this proof involves going back to the basic results of automata theory, the basic process of translating a formula in weak S1S into an equivalent automaton, and just making sure that all of those proofs work as consequences of our proposed axiom system. This is really tedious, so I'll skip out on pretty much all of the details. I'll link my PhD thesis down below if you're interested in going into more detail with this. But the real proofs that are going to make these really quite trivial are showing that deterministic finite state automata and non-deterministic finite state automata are equivalent, and also that bounded and unbounded automata are equivalent. That is to say, our construction for turning a non-deterministic automaton into a deterministic automaton is an equivalence as a consequence of our axiom system. And also that our process for turning an unbounded automaton into a bounded automaton is also an equivalence according to our axiom system. That later step, our process for bounding and unbounding automata, is actually really quite simple. We're just trying to show that various automata behave correctly, and in order to do that, we simply need to write out a formula for the set of all positions where the automaton doesn't behave correctly. Therefore, the set of positions where the automaton doesn't behave correctly is a set in our model, and therefore has a smallest element. So there's a first instance where the automaton doesn't behave correctly, and you can show, well, that's absurd. The determinization result, however, is a little bit tricky. Remember that the goal of our power set construction was the state of our power set automaton should be the set of all states at a particular time that are reachable from a start state by reading the input characters that we've seen so far. If you have a run of your non-deterministic finite state automaton that ends in a particular state Q, then you can show that Q has to show up in the state of the power set automaton at that particular time. We simply use our Boolean operations to construct the set of all positions where that doesn't happen, and again, this has to have a smallest element, and we can prove that it's absurd that it has a smallest element, because if our power set automaton is working at time x, then it's working at time x plus 1, and of course it's working correctly at time 0. So again, induction proofs that require us to describe the set of all counterexamples as an actual set within the model. So we've shown that every reachable state shows up within the state of the power set automaton, but what about the reverse? Is every state that shows up within the state of the power set automaton actually reachable? To prove that is a little bit trickier. We need to construct a harvesting automaton that reads in the run of the power set automaton and outputs a run of the original non-deterministic automaton. This automaton can be made to be reverse deterministic if we give it a special state that says, oh, something went wrong. Because this automaton is reverse deterministic, the run for that automaton has to be in the model as well if the inputs to the automaton are in the model. And then we just take a look at the set of positions where this harvesting automaton is in a failure state. This set has a largest element, and that's going to correspond to the first time as the automaton is going backwards that it fails. And you can show, well, at no point should it fail to find a run. If the harvester can work up to a successor of x, then it can work up to x. And so by using a reverse induction, you can show that provided that the power set automaton actually did accept, this harvester is going to find a run for the original automaton, completing the proof that our original non-deterministic finite state automaton was equivalent to the power set automaton that we hoped it was. So that's the hard part of showing that our axiomatization is complete. Again, you can find details about this proof in my PhD thesis. But once we've done that, we've actually done most of the work towards proving that our various proposed non-standard models are actual non-standard models of weak S1S. A lot of the important work is getting done in showing that we have a complete axiomatization here, and that saves us from having to redo this work over and over and over again every time we want to show that a new structure is a non-standard model of weak S1S. In my next video, I hope to use my axiomatization to prove that we can have non-standard models of weak S1S with any woozle as their first-order part. Specifically, the first-order part is going to be an arbitrary woozle. The second-order part is going to be the collection of sets that are piecewise periodic, once we've defined a notion of periodicity on the woozle. And most of the work there, it will just be showing that our models are closed under run maps and reverse run maps for automata. So making sense of what it means to run automata where the inputs are words of woozle length. Another really important question that we can ask is, our axiomatization is countably infinite? If our axiomatization only had finitely many axioms in it, we could AND them all together and get a single axiom that axiomatized weak S1S. But these are countably many axioms, and so we can't and them all together. One of the questions you can ask is, well, is there a finite axiomatization? Can we fundamentally reduce the size of our axiomatization somehow? Or is there something about this structure that means we have to have countable axiomatizations? And I hope to address that question as well in a future video. So I hope that you'll join me for those, and leave any questions or comments down below, and I hope to see you then.